Alright, so in this video I'm going to be explaining another important article with the title Source-Free Domain Adaptation via Target Prediction Distribution Searching. This paper in 2024, Journal of Computer Vision. Existing source-free domain adaptation methods typically adopt the feature distribution alignment paradigm via mining auxiliary information, for example, pseudo-labeling, source domain data generation. However, they are largely limited due to auxiliary information is usually error-prone while lacking effective error mitigation mechanisms. To overcome this fundamental limitation, in this paper, they propose a novel target prediction distribution searching paradigm. So they prove that in case of sufficient small distribution shift, the domain transfer error could be well bounded. To satisfy this condition, they introduce a flow of proxy distributions that facilitates the bridging of typically large distribution shift from source domain to target domain. This results in a progressive searching on the geodesic path where adjacency proxy distributions are regularized to have small shift so that the overall errors can be minimized. So existing source-free domain adaptation methods rely on mining auxiliary information. You see the paradigm comparison in A here, that you see conventional feature distribution alignment versus B, that we have our target prediction distribution searching for matching the ideal target distribution. This searching is driven by a progressive search strategy with error control. So it's like a searching strategy. But in C, we construct a flow of proxy distributions with sufficiently small shift. So their shift is very close. Shift from here to here is very close. Again, very close. So we are moving in a path. It may come back to the original as well. So, and indeed, we see that considering P sub S and P sub T as two different points in a metric space. So we are looking at distributions as points in a metric space. This is the framework that we do in functional analysis in mathematics, in modern versions of reproducing kernel Hilbert spaces. So it's very easy to understand. Even when you approximate distribution with, for example, KL divergence and those things in probability that we have talked about it, we are looking at distribution as points, not just a function. It's just a point in the metric space. So we can look at it as a searching. We go from one distribution to another until we reach our target distribution. We start from the start distribution, then we move. So it's very interesting. So in transfer learning, the most relevant work with ours is gradual domain adaptation, performing knowledge transfer in time dimension. Existing progressive transfer methods for domain adaptation can be split into three groups. The first group is subspace-based. assuming that the source and target domains are 2 points on a manifold. For reducing their domain gap, subspaces along geodesic path are interpolated to connect 2 points. The second group is gradual learning based, for example, curriculum learning. This is, of course, you can use all techniques of active learning for curriculum learning, because the only difference between curriculum learning and active learning is that active learning, we are interested on unlabeled data. We want the model suggest which of these labels are near the boundary, which have low uncertainty, that they should be labeled. But in curriculum learning, we assume that we have all labeled data. We don't worry about unlabeled data, and we just find the hardest example and work on that. It's like model editing, that you freeze some weights of the model, and then for some hard examples, like in self-driving cars, you don't want to kill a passenger or pedestrian, somebody who is walking, and then you add or modify. So this is the addition, and then so just with this addition, the KL divergence between predicted distribution of original and the edited model, they should be the same. So the KL divergence should be small between the two distributions. So this is the group of gradual learning. You're gradually learning it, like deep clustering. In epoch-wise training, they use the previous epoch to guide the current training epoch. But the third group is interesting, the domain generation based. The core idea is to generate a flow of intermediate, smoothly shifted domains capable of bridging the gap between the source and the target. The source and the target domains. So importantly, we highlight the key novel designs in comparison. We form the intermediate domains with simple yet reliable probability distributions. We uniquely take into account error control through the progressive learning process. Our formulation is tailored for source-free domain adaptation. So for target prediction searching, unlike conventional feature distribution alignment, we reformulate it as searching the optimal target prediction distribution. We start with the initial prediction distribution obtained by applying the source model theta s. The objective is to identify the ideal prediction distribution, which is unknown, typically different significantly from the large, which has large distribution shift, for example, with a source, and we formulate it as a distribution optimization. This D measures the discrepancy between the two distributions. And these theta are the parameters to be learned. So two key challenges for this optimization, and of course, SE is our searching process. So our D has become searching the problem. But the two key properties for this optimization are that P sub T is unknown, making it hard to optimize. So how do you know this? So you don't know. To overcome both, and the second, of course, problem is domain gap between them are large, making one-step search hard to achieve good result. So to overcome both of these two challenges, the 1 and 2 that I said, inspired by the spirit of gradual adaptation, this paper, we designed a progressive search strategy. Especially from the distribution P from the source to the target, we construct a proxy distribution flow where the start is just source theta s and the end is your you want to go to the target. So theta k is P of theta target. So, considering SFDA is a classification orientation problem, so they use Wasserstein inference-based measure. So using this Wasserstein distance-based measure, they can see the maximum of these for any adjacent proxy distribution. The measure of the shift for C-way classification is this. And this W infinity is just a Wasserstein infinity distance. Random variables x1 and x2 stand for samples from the previous distribution and the next distribution. And of course, their labels respectively. And while the measure in this equation, while the measure presented and the theoretical result, with this measure, we derived the following theorem for transfer performance upper bound of our progressive searching. So don't forget, we are looking at what is the next stage. We are searching the next distribution that is very much closer to the original. Then we move one step. Then again we move one step. We move until we reach the unknown target distribution. But there is an upper bound. There is an upper bound. The upper bound is this one. This is bounded by this, which we should see what is that we can reduce it. So L is the objective loss as learning for p t sub k prediction. This R here stands for the regularization strength of theta sub k. So if the source model has low loss, greater than a threshold, then this loss is upper bounded by this. And of course, N is this N here you see is the size of the target data set. Together with the aforementioned geometry principle, we realized the proposed learning strategy by transforming the original optimization to the following k subproblems. This defines a search process along the geodesic path. Now we are talking about single-step searching. A single-step searching is driven by aligning the adjacent distributions, namely minimizing distance between previous distribution and the next one. In practice, we do not adopt the original definition to estimate this distance. So we need to iteratively compute the Wasserstein infinity distances of all C categories and take the maximal one as a distribution shift. However, in our context, no accurate category information is available. To solve this problem, we propose to minimize all distances without the need for the category information. This leads to the following reformulation. This category agnostic formula allows us to compute the distribution shift in an unsupervised manner, facilitating the subsequent analysis for shift reduction. So in this figure, you see the alignment from distribution from P to Q, from this P to Q. You see the transport, you see the alignment. Using data pairs with neighbor relation. For example, in A here, you see that due to neighbor constraint, the cross-distribution data pairs can be divided into A group, this A group, with same category, and B group with different but related category. And in B, you see that the transport over these data pairs encourage P of C equal to 0 aligned to a wider distribution. And this Q tilde C equal to 0 is our wider distribution, which covers the real target distribution QC0. So the proxy distribution flow is supposed to converge to the ideal target distribution progressively. It's like a path. At each time, we move just a little bit from one distribution to another distribution. And don't forget that these points are points in a metric space. It's not a Euclidean, it's a metric space. So you need functional analysis to understand it. You need topology over functions. So during the transfer process, all models, including the source model and all intermediate models predicting the proxy distribution, have the same composition. So it consists of a feature extractor and classifier, ending with ending softmax operation. And this means the function composition. So we use two neural networks. The first neural network is a deep architecture. It's just a feature extractor. The second one is a 4-layer network, which we use it as classifier. So you see the overview of the pairwise alignment from the previous distribution to the next one. The two steps are involved. First, we have shift estimation, generating sample pairs across two distributions by chain-like search. The second one is shift reduction, pooling the sample pairs found by maximizing the mutual information in the prediction space. So we are given the pre-trained source model, target data, and then we go through two loops, nested loops. First, we initialize model by the train of the previous weights. Then we generate the credible group. Then we sample a mini batch. We construct data pairs, estimating the distribution shift by credible sampling. Then we do forward propagation. Then we update through the distribution shift reduction. And this distribution shift reduction is important, so we should talk about it. We use the following objective to reach the goal, where I is the mutual information here, whose composition is the same as this paper. So L sub W, this loss, is sensitive to target data scale. When the scale is small, since the limited data cannot describe the probability distribution well, the optimization effect based on single regulator is restricted. To overcome this approach, we introduce the diversity loss, encouraging the balance of category prediction. This skill is widely adopted by unsupervised approaches for multi-way classification to avoid the solution collapse. So the model predicts all data at some specific categories. Suppose that theta sub k transforms x sub I to probability vector q sub I. So this loss becomes L sub b. And KL is just a KL divergence loss function, and between a uniform distribution and your q sub c, which is the probability of x sub I is in the cth category. So we combine them, the regulator and this L sub b, we get the total loss. And beta sub n trades off the two regularizations. Its value is related to the dataset scale. The smaller the dataset scale, the larger the beta sub n.